Let's take a look at this robot with a bright green light.
Begins our Red Alliance 2 level 4 Coral up already in just the first few seconds. 58.95 going back for more from the Coral.
It's moving so fast, and it's arriving so precisely.
Coral Station a second and working towards a third. Our Blue Alliance, meanwhile, we've got 2 Coral up from the 1640 machine.
How did they do it? Hi, my name is Gene and this is my dog Rubble. I'm one of the mentors on the team and I actually moved to Poland about a year ago and I don't have any robots in here. So I'm just gonna give you a quick overview and then our students will take over from New Jersey. They will show how to do everything on a real robot. Here in this elastic dashboard we're running a simulation of what the robot was doing. So this is a picture of the field. This little red square is the picture of the robot, and if you push the button on the joystick, same button that you were pushing in the competition, the robot runs a trajectory. And the reason it's able to move so precisely is because the robot always knows its X, its Y, and which way it's facing or heading. Push one button, it goes here, push another button, it arrives precisely where it needs to be. If you guys have not tried the elastic dashboard, if you're still on smart dashboard for example, then maybe take a look. I think most of the teams are switching to elastic from smart dashboard these days. What you need to do is, it's very easy. Just Google up, download elastic dashboard FRC. Then click on their GitHub page and here in the bottom right corner you will see releases. Click on releases like this. And wow, they have another version, 2027, that's interesting. But in any case, you can pick the version that you like. For example, maybe I want 2026. Go under this version, you will see assets. You can open up the assets and pick whichever one installer you want for your operating system. Maybe Windows, maybe macOS, maybe Linux, maybe web-based, so I'll be picking Windows. And download and give it a try. This is the secret. If you want your robot to move quickly and precisely, the robot must know its X and its Y all of the time. And Limelight camera can help with that very easily. Now, in order for the robot to know its X and Y, this Limelight camera, or better 2 or 3 of them, have to be installed on the robot. This is what the students actually did. They took their robot, it's not exactly like this, but that's the picture I have. And then they installed 2 cameras on it. One in the front, so that it sees the tags from the front, and the other on the left side, like this, so that it sees whichever April tags are available on the left. What's important is the exact locations of the cameras. So the camera 1 was installed at x1, y1 of 0.40 minus 0.15. Remember, in FRC your x-axis goes up and your y-axis goes to the left. And so because this camera was to the right, it had a negative y, minus 0.15, and a positive x, 0.40 meters. Every little square here is 1/10 of a meter. And this other camera that's pointing left, of course you can see it had an x2, y2, where x2 is 0.20, 2 squares up, 1, 2, right? 1, 2. Positive x, and it had a positive y of 0.32 squares. 1, 2, 3, and another 0.2 in here. Once they had 2 cameras installed on the robot, the robot can see a lot of tags. And you also need to specify which way the cameras are looking. So forward is 0 degrees, right? Left is plus 90 degrees on FRC, and if you have a camera that's facing to the right, then it would be minus 90 degrees, because left is plus 90, right is minus 90, right? What we do when we specify the camera locations is we say that the camera 1 has a pose. Pose is 3 things: X, Y, and which way it's facing. So the X of this camera is 0.40, the Y of this camera is minus 0.15, as you can see, and the heading is 0, north, it's facing forward. And as you guessed, camera 2 has a different pose. X of 0.2, y of 0.32, and it's facing to the left, so heading is plus 90 degrees. That's what you need to remember to keep in mind for your cameras when you want to set up localization on your robot. Because I have moved to Poland about a year ago, these are the actual students in New Jersey from Team 714 who did the real robot setup for this video. Ariana, Randy, Eric, Enrique, Joshua and Fernando, thank you so much for making it happen.
So on our YouTube page, we have a code example for swerve driving, right? If you go to our YouTube channel, 714 Robotics, and you go down to video number 6, which is right here, video number 6. We have a link. We have a link to our GitHub where the example command code, swerve code is. All you do is you code the GitHub. You go to PyCharm. Virtual load. And you clone repository. You paste your link in. Clone it. Give it whatever name that you want. You could name it Swerve. I already have it downloaded, so I'm just gonna use the one I already have downloaded. Anyway. Let me remove this from the list. Recode. Okay, before you connect to the robot, actually, make sure everything you need is downloaded. So make sure your virtual environment is downloaded. And after that, install all the requirements, all the packages that you need to actually run the code. So while you wait for that to... Okay. After your requirements are installed, while you're still connected to the internet, you should go to sync and then run sync. This basically downloads all the actual libraries from the internet onto your computer. Okay, so while it's syncing, it's asking us to update to this version of RoboPie. We just click Y, enter, and it continues to download. Okay, so after you download everything and you sync to your computer with internet, all the steps before that I've mentioned, you do with connected to an internet of sort. Now you can connect to your robot. Now you can connect to your robot. Well, the robot's host name. For us, it's 714, so we enter that, and then we're able to deploy it. Some robots, well, every robot is different because your team number is going to be different, but yeah.
So, if that's true, then
Anyway, now that we're successfully deployed the code, we can go to Edge Elastic to see the heading, the Y, and the X.
Thank you, Enrique. Let me take over from Poland for just a little with some theory. We were in this drive subsystem code file, but if we go back to robot container, let's actually set up the Limelight cameras for localization. Here, if you go to robotcontainer.py, you will see the init function. This is where you add all sorts of robot subsystems, the drive subsystem, the arms, the whatever else your robot has. Here is where you add Limelight cameras to your robot if you can. This is an example code. It's commented out, meaning that there is the pound sign in front of it. It's called commenting out, and it means that the code is disabled. I'm going to enable it, uncomment. So now I have added the front camera to the robot. And make sure that your camera has the name Limelight-front, or you can give it some other name on the actual camera and then put the same name here in the code. If you want this front camera to be used in robot localizer that gets you the X and Y, here is what you need to uncomment. These lines below. So we say Limelight localizer dot add camera, and we add our front camera. And remember, we talked about the position of the camera on the robot. This is where we need to provide the camera position on the robot. We say camera pose on the robot equals x of 0.4, y of minus 0.15, and z of 0.5, because it's half a meter above the floor. And we also must say that the camera is facing forward. Forward meaning 0 degrees. Remember, for the front camera, x was 0.4, y was minus 0.15, and the heading was 0 degrees, which means straight forward, pointing forward. Now let's add the other camera, camera 2, it's the left camera. So its x and y are 0.2 and 0.32, and it's heading left, which is plus 90 degrees. So let's go to the code, and let's copy the addition of the front camera. So we're just gonna call it left camera, Limelight, left. And let's also add this left camera to the localizer. So we're going to say Limelight localizer dot add camera. Then we're gonna say that we're adding the left camera. And the x and y for the left camera were different, right? The x was, I think, 0.2, the y was plus 0.32, and z was 0.5, it was also half a meter above the floor, and it was actually looking left, so that's plus 90 degrees. This is it. This is all you need to add Limelight cameras into robot localizer so that you get the x and y from them. This is literally it. Did I forget something? Yes, I did. In order to know its location, the robot also needs to know which way it is facing. And for this, most teams use a gyro, which usually is the Pigeon or Navex, or some other gyroscope. There are plenty of awesome gyroscopes right now available to FRC teams. For example, if the robot thinks that it's facing south, but in reality it's facing north, or to the right, or to the left, then the x and y will not be correct. So if you go to the actual robot code, to robotcontainer.py, and scroll a little bit down, to the function where all the buttons are defined. Normally all teams call it configure button bindings. You will see that the POV up joystick button, which is, I'm sure everyone knows what where different joystick buttons are, but POV up is this button, and POV down is this button. So POV up button is here, and the code says that if POV up button while it is pressed, the robot is getting reset to be facing north. North meaning 0 degrees, north of the field. And if POV down button is pressed, this one, driver controller, driver's joystick, POV down, then to this button we have bound a command to reset the robot to face south, so that we can set up the robot's facing direction or heading. Let's see how this works in simulation. So we switch the robot to run in simulation, and we say run. This is the robot simulation window if you have never played with it before. We say enable the robot by switching to the teleoperated state. And let's go to our elastic dashboard. Okay, it was connected to the real robot. If you want the elastic dashboard to connect to the simulation of the robot, to the simulated robot, you simply need to click on settings in here and then switch from real robot 10.team.2 to the local host, which is the simulated robot. Close. So the simulated robot right now, as you can see, it is parked here on the bottom of the field facing north, heading of 0, north of the field. Now if I push the POV down button, look what happened. Robot is now thinking that it's facing south because its gyro, its simulated gyro, was reset to be 180 degrees, which is facing south of the field, right? And if I push the POV up button, the robot gyro is reset into thinking that it's facing north, and the X and Y is also reset as you saw in the code. Down, up, down, up. If you want your X and Y to be determined correctly by the cameras, you need to make sure that the robot has the correct idea of where it's facing, where it's heading, its orientation on the field, south, north, west, east, or whatever, in the beginning of the game. Now let's stop the simulation and connect our elastic dashboard to the real robot that we have sitting on the school field in New Jersey, which is beyond visual line of sight for me. But the way you connect your dashboard to the real robot is you go to settings and you say IP address 10.team.2 and close. The actual physical robot is now sitting in this point of the field and it's facing south. But because its gyro has not been set correctly, it's thinking that it's facing north and the cameras are not picking up the real X and Y of the robot. What we have to do is we have to ask the guys to push the POV down button on their joystick. And watch what happens to the X and Y of the robot once the robot orientation becomes correct. Hey guys, can you push the POV down on the joystick to make the robot face south? Wow! The moment the robot started to face south, the X and Y of the robot started to move, eventually converging to the real actual position of the robot on the school field. So, how does this make you win any actual games in the competition? Let's talk about it. Once you have the X and Y, you can actually make your robot run a trajectory. Let's go and look at our configure button bindings function again. So we have talked about two buttons that set the robot orientation to be north or south. And by the way, you can add more orientations, right? You just need to copy and paste. Reset south, reset whatever, you know. And just bind it to some other button, not POV down, but maybe POV left or POV right or whatever, right? Now let's take a look at running the actual robot trajectory. Binding a command to a button is very easy. You first need to create a command, for example trajectory command, then you need to pick which button you're gonna bind this command to. For example, in this case, let's make it Xbox controller button A. So button A on our joystick will be bound to this trajectory command. If you look at the coordinates very carefully, it's starting from x1, y7 and minus 54. This is the feeder. And then it goes to the endpoint in here. In another video you can see how you can create new trajectories using the path planner, but imagine you already have the x and y for your trajectory waypoints. Then this is how you can bind it to a button. This example code is available when you download what Enrique told you to download. So while the A button is pressed on the joystick, the robot will be driving this trajectory. And also you can reverse this trajectory. You can say trajectory command.1.reverse. And let's bind it to another joystick button. The button B on the joystick. Xbox controller button B, right? I'm sure everyone knows, but on an Xbox joystick this is where the A and B buttons are. Let's see how these trajectories work in simulation. In simulation, now I need to push the A button, and the robot is running the trajectory. It's approaching the reef precisely. Pushing the B button, and it's going back to the feeding station. Pushing the A button, it's running the trajectory to the reef. Pushing the B button, and it's going back to the feeder quickly and precisely.
Begins our Red Alliance 2 level 4 Coral up already in just the first few seconds. 58.95 going back for more from the Coral.
I hope that the setup of Limelight localization for you will be just as easy. Keep in mind that the code examples that we provided work for Limelight 3G, they work for Limelight 3, and they also work for Limelight 4. Limelight 4 and 3G will work a little faster, but maybe you will not even notice the difference. Also, in the description of this video you will find an example for the tank drive robot. If you happen to have a tank and not a swerve, everything should still work. In the next video, our students Enrique and Fernando will show you some practicalities about setting up the Limelight camera, such as uploading the map and tuning your gyro for the best performance. Until then.